All right, let's take a look at water rockets. It's probably one of my favorite things to do as a STEM project and to analyze. And what we're going to do is we're going to look at the thrust phase, the ascent phase, and then the descent phase. Okay. We're going to calculate and look at forces, and then we're going to use Bernoulli's conservation of mass isentropic process relationships to find the exit velocity of the water. Okay? Then I will show you a programmable or program code that solves altitude thrust for a water rocket. Okay? So let's first start with the thrust phase. Thrust phase. Okay, so here is a rocket. And let's say there's fins on it. I won't put it right there. And it's somewhat filled with water. Okay? Now, let's assume upward is positive y. And inside here would be your pressure, P naught. And let's look at the forces. So I'll just draw them right here. Well, you're going to have thrust, you're going to have weight, you're going to have drag, and it shoots out, we can call it UE, okay? Or U. Let's call it just U because that's how I have it. So basically you pump air in here, you pump it to a pressure, PSI, say 65 PSI, and then you launch it. And what's going to happen is the air inside is going to expand, the water's going to shoot out, and the pressure inside is going to drop, and therefore you can get thrust. Okay? So, if we sum the forces in the y, get MAY, positive is up, so we get thrust, minus weight, minus drag, equals M dv dt. And we're going to only look at 1D motion, just vertical, straight up, and straight down. All right? Now, from previous, you know that thrust is m dot times u, the exit. The weight is mg, and the drag is 1/2 rho, the water, v squared cd times a times the mass dv dt. Okay? Now, the mass, m, is technically the mass. I'll put a little note here. So m is the mass of the rocket plus the mass of the water plus the mass of the air. However, the mass of the air can be neglected in this point here because it's so small compared to those. Okay? So I'm going to divide by m so I can have a solution for dv dt. So we get m dot over m dot over m times u minus g minus 1/2 rho w v squared cdA over m. So that's our thrust phase. Okay? And I'll put a little line here. And if we do the ascent up to the apex, so it'll slow down and reach a velocity of 0 before it starts falling down. It's the same free body diagram, but you just no thrust. Okay? So minus mg minus 1/2 rho w v squared cd times a m dv dt. So we get dv dt equals minus g minus 1/2 rho w v squared cdA over the mass. Okay? So this is ascent. Let's look at descent. Now, this one, I'll draw the free body diagram up here, and I'll just do it as a simple rocket. Okay. Oh, I should go back that way. Let me erase those. Oh, where did that go? There we go. That is a terrible rocket, Dr. Craig. There. So here, downward is positive, and we have drag, we have weight, and then that's our, so we have W minus D equals M dv dt, because we want to make sure acceleration's in the positive direction. We get mg minus 1/2 rho v squared cdA equals m dv dt. So we have dv dt equals g minus 1/2 rho w v squared cdA. Okay, so you notice these are different. So we have three sets of equations that we're going to have to solve. Okay. Now, what we're going to have to do is we need to solve for this exit velocity u. Okay? And how we're going to do that is pretty much with three to four major equations. All right? So, finding u for the thrust phase. So we're going to use Bernoulli's. We're going to use conservation of mass, and we're going to use isentropic equation. Okay? So let's do Bernoulli's first. So Bernoulli's is from this point right here, 1, to the exit 2. All right? It relates fluid energy. So we have P1 plus 1/2 rho V1 squared plus rho GZ1 equals P2 plus 1/2 rho V2 squared plus rho GZ2. Now, we're going to neglect these change in altitudes. And this is P atmosphere. All right. And now what we're going to do is conservation of mass to find the relationship between the velocity inside the bottle to outside. Okay. So we know that m dot 1 equals m dot 2 at steady state. Flow rates in equals flow rates out. So we have rho W pi. We have rho W A1 V1 equals rho W A2 V2. The densities will cancel. So we have pi d1 squared over 4 times v1 equals pi d2 squared over 4 times v2. The pi's cancel, and we can solve for v1 in terms of v2, which is d2 squared over d1 squared times v2. All right, we're going to plug that into here. So let me do that. So now, and let me do that right here so I can see everything. P1 plus 1/2 rho V1, which is D2 squared over D1 squared times V2 squared. This is all squared, right? Okay. Equals P atmosphere plus 1/2 rho V2 squared. All right. Now we need to find this. And we're going to use isentropic equations. Which states that P over P naught equals V naught over V raised to the K. This is for air. So therefore P1, which is P, is going to be P naught, V naught over V. So these are V's. Okay, where V naught is your initial, V is your volume at a given time. It's same with P1 and P, that's pressure at a given time. And the P naught and V naught are your initial volume and initial pressure. Okay, so let's go ahead and plug that into the equation above. So we have P naught, V naught over V raised to the K plus 1/2 rho. This would be D squared to the fourth over D1 squared, or sorry, D1 to the fourth, V2 to the second equals P atmosphere plus 1/2 rho V2 squared. All right, let's check to make sure we got all of this right. Yep, okay. And what did we call V2? Well, I'm just going to erase it. We called it U, right? So I'll just change that to U. And we're going to solve for U now. So U becomes square root, we got denominator and numerator, 2 P atmosphere minus P naught, V naught over V raised to the K. Then we have density, D2 over D1. This is to the fourth minus 1. So this is our exit velocity that we need to use. So just to recap that, we had to use Bernoulli's from inside the bottle rocket to outside. So we had to use 3 sets of equations: Bernoulli's, conservation of mass, and isentropic process to determine the exit velocity as that water shoots out. Because the water level inside the water bottle will go down, the water will shoot out, and the air will expand. So this isentropic process is dealing with that expansion. Okay? All right. So now that we have 3 sets of equations, we have our exit velocity, what we can do is we can use a numerical method, and I'll upload these codes. So let me show you. Oh, not that one. Let me show you, is it this one? Yes. Okay. So here is a program that calculates altitude and some thrust characteristics for a water rocket. All right, so let me run this. And it actually uses 3 function codes, the thrust phase, the ascent, and the descent phase to find all these. So this is the acceleration just for the thrust phase. This is thrust, m dot, and the mass of the water as a function of time. Here is altitude versus time, okay? And then the last one is velocity as a function of time, okay? All right. Okay, so how does this work? Well, first, I have global variables. These are pretty much constants that are in my function codes, and I'll show the function codes here in a little bit. Okay, here's my givens. I picked coefficient of drag, air density, water density, specific heat ratio, initial pressure inside the bottle. I converted that, atmospheric pressure, exit pressure, the rocket diameter, rocket area, nozzle diameter, nozzle exit diameter, area. Okay. Let me fix that. That would be area. Okay. I just changed this to the rocket area from AR to S, just for me. Acceleration due to gravity, the volume of the bottle, so 2 liters. I converted that to meters cubed. These two is initial water value, initial air value, and we can get rid of these. So you can change these and mess around with the data. Okay. Mass of the rocket without water, total mass of the rocket. Okay, and again, I neglected the air because it's not going to be it's not going to add much. And then initial air volume. Okay. Then I'm using a numerical method called Runge-Kutta. I believe it's a 4th order Runge-Kutta method. Don't worry too much about that. Okay. But the way I'm doing this is I'm actually changing the water height or the water volume by a small amount, and then determining, okay, what is that time step, and doing the numerical method that way. Okay. So here's the initial, we need some initial conditions. So initial water height, initial velocity of the rocket, initial time, the mass of the rocket, loop indicator, and initial altitude. Okay. So what I'm doing is changing the water level in the bottle, looking at all of these parameters. Okay. And I'm doing that step by step by step until the water is gone. Okay. So first I need to calculate the exit velocity, which is, I just derived that equation for you. Calculating the mass flow rate based on that exit velocity, which I'm then calculating the thrust. If I calculate the volume flow rate of the water going out, I can take that and have H, which is our volume that we're looking at for our time step, to figure out what our time step is. Okay, so this is meters cubed divided by meters cubed per second. That gives us a time. Okay. Here's the mass of the rocket, the drag, and the mass of the water. And then here is, I'm sending this information 4 times, and it's going to find an average down here. See how it's 1/6 of this average to this function code, which is this numerical method. Okay. Don't get stuck on this. As long as you kind of understand what's happening, that's perfectly fine. So the function codes are here. Let's see, that's the ascent. I'll do that here in a second. Let me get this one. Nope, that's the descent. And last one, I guess, is the thrust, which is where? Do I have that one open? Yes, right there. Okay. So here's a function code. This one calculates and uses that dv dt equation that I showed you for thrust. Okay, this is that minus g. This is your thrust term. Here is your drag term. And basically, I'm running that, getting an average, and it's getting sent back to the main code, which is here. And we do it 4 times, and we take some sort of average with it. Okay, it's a very stable, promising numerical method. Okay, and then here is I take the initial water volume and I subtract that, and then I can basically, this is a loop, and it's going to keep doing that. It's going to keep subtracting this amount and telling us, okay, what is the velocity? What's the exit velocity? What's the velocity of the rocket? What's the new water volume? And so forth. Okay. Then down here is I do a Runge-Kutta method again for the ascent. Okay. So here, instead of volume, this is our time step. Okay. So we're now doing a time step. And the ascent is right here. All right. Again, this is that dv dt equation that I showed you. And then finally, we're doing it again for the descent phase. Again, numerical method based on the descent phase, okay, where you have this dv dt equation. And if you notice here, so if you're using global variables, these are constants, you need to put global up here too, because these are the constants that are in here that aren't changing. So once I do that, then I plot everything, okay? So I will upload these as a zip folder for you, so you can mess around with some of these numbers and it should work. So let me run this again. And so like, okay, so 25 meters, and let's make this 0.6. And so if we add more water, then it'll go up to, what's that value? Probably like 28 or 29. But say we run this at 0.1, not very much water, then it only is like 19 meters. Okay, so you can mess around with all of these parameters. Let's go up to 100 psi. Okay, and you get different values. So we go up to like 22.5, close to 22.5. Okay, so you can look at all of these cool little parameters for the water rocket. What happens if we lower the drag? So say 0.1. Then we can go a little bit further, 85 meters. Okay, so it's cool. So you can mess around and say, okay, I'm going to make a nose cone that has lower drag. What's going to happen? What happens if we don't use water? Say we use something else. We can change the density. Okay, change the pressure inside. What happens if we use a bigger bottle? So we can change this to 3 liters or something. Okay, what happens if we add fins? That's going to change the weight of the rocket. Okay, so you can use these as an initial preliminary test to figure out how high the water rocket's going to go. All right, I hope you enjoyed this and have fun.